Right, hello and welcome back everybody. So we're moving on to the next section, which I'm calling the discrete derivative, but it has a subtitle, finite differences. So kind of in the broader realm of mathematics, finite differences is what you'll hear, and we'll see what this is in a little bit, but it really should be thought of as a derivative for sequences, or rather a derivative-like object maybe, for sequences. Because that's really what we're going to be spending really the rest of this chapter on, is defining a derivative for sequences, looking at similar derivative rules for sequences, looking at the antiderivative or the integral for sequences, and then the common rules of this integral for sequences. So that's where we're headed. Let's just jump right into it then. What is a finite difference? Well, we're going to start, just like I said there was a derivative operator, there's also something called the difference operator. And the difference operator, you probably did actually see this operator in calculus, because you would start to learn slope, m equals delta y divided by delta x. This was the quote-unquote change in y divided by the quote-unquote change in x. And if you do this over the unit change, unit meaning 1, that is actually the finite difference operator, or the difference operator. So it's defined as, using this Greek capital delta of, and you can define this on a function, so delta of a function of x, whether or not that x is in the integers or the real numbers, or even the complex numbers. You simply take x and you add 1 to it, so we've kind of shifted forward by 1 unit, evaluated that inside of f, and then subtracted the earlier, or the original f on the x without a plus 1. And why is it called a difference operator? Well, there it is. You're taking the difference of a function that's been shifted just by 1 unit with the function where it is. And a lot of times this is actually called the forward difference operator, because we could technically define a backward difference operator. Maybe I'll call it subscript b. This would be the backward difference operator, where you actually look at the function right away and you're taking the difference with where it used to be. So you subtracted 1. So forward difference, you're looking ahead, maybe into the future, to the right. Backward difference, you're looking into the past a little bit. We're just going to call it the difference operator, or the finite difference operator, for this entire semester. And if we actually define the object which has already acted on a function, delta f, that's called the finite difference, or the finite difference of the function f. Now, of course, the whole point of this chapter is that we're working with sequences. You can certainly define these on sequences. You're going to shift the sequence forward by 1 and subtract where it used to be. And that's, of course, called the finite difference of the sequence as well. So let's compute a couple of these. Maybe looking at the case x squared plus 2x minus 1. The finite difference of f is going to be evaluating f on x plus 1 and then subtracting f on x. This is going to feel very similar to the limit definition of the derivative, right, where we had epsilon there. Maybe if you're taking a different class where you have an h there, it should feel very similar. We're just going to work with the number 1 rather than epsilon. So we're going to evaluate f on this argument x plus 1, which means all of the x's that show up in f, I'm actually going to replace with x plus 1 and with x plus 1. And so we're looking at x plus 1 squared plus 2x plus 1 minus 1. So that's me evaluating the function on x plus 1. I'm going to go ahead and subtract the function evaluated just on x, which is itself. At that point, I'm just going to simplify. I mean, technically, if you were just asked to complete a problem on this, and your instructor weren't worried about you simplifying or anything, go ahead and leave it like that. Of course, it's going to make more sense if we do simplify. A lot of things should cancel the same way they always do with derivatives. So let's go ahead and FOIL out something like x plus 1 squared. I'm going to have x squared, that's the first terms multiplied together, and then combining the outside multiplications, which would be x and 1, as well as the inside multiplications, which is also x and 1. I'm going to have 2 copies of x times 1, also known as 2 copies of x, and then the very last terms are going to be multiplied to give me 1. So that's FOILing x plus 1 squared, and then I'll just distribute the 2 to both terms here. I have 2x plus 2, and my minus 1 is coming along for the bride. If I go ahead and kind of combine all of the terms that are possible here, I've got 2 copies of 2x, so I've got a 4x there, and then I've got a plus 1 plus 2 minus 1. Those are going to combine to a plus 2, and if I distribute this minus sign to all 3 terms, that's what's going on the right there. And then one more round of cancellation, cancel the x's. 4x minus 2x gives me 2x, plus 2 plus 1 gives me plus 3. You kind of actually see out of the finite difference what would happen if we took a derivative of this. We would actually get, 2x plus 2. So this is really close to the derivative. We're getting 2x plus 3 instead, but in some ways it really is an approximation to the derivative. If we act this on sequences instead, maybe I'm looking at the sequence nq minus 2 to the n. I'm going to do the same thing. I'm going to shift my sequence forward by 1, and then I'm going to subtract where it currently is. If I shift forward by 1, I'm replacing every n with an n plus 1, and this n as well with an n plus 1. That's going to give me this term, n plus 1 cubed, minus 2 to the n plus 1. And then I'm going to subtract the sequence by itself, which is just subtracting n cubed minus 2 to the n. Once again, I can simplify everything. Let's go ahead and be a little bit smarter rather than working harder. We're just going to use the binomial theorem and remember Pascal's triangle. I actually have quite a few of these rows memorized in my head, but at the very least, there's a 3 in the power here. Let's look at the third row, 1, 3, 3, 1. Pascal's triangle says that the expansion of n plus 1 cubed is going to be 1n cubed plus 3n squared plus 3n plus 1. And then if I want to simplify something like 2 to the n plus 1 using exponential rules, I can do 2 times 2 to the n. The only reason I'm doing that is because what's left over on the right-hand side is 2 to the n. So I'd rather write that in terms of 2 to the n. Okay, then I can go ahead and distribute this minus sign to both terms there. That'll give me a minus n cubed, which will cancel with that plus n cubed up front. I'll have a minus 2 copies of 2 to the n and a plus really 1 copy of 2 to the n. So that's going to be 1 minus 2 total copies of 2 to the n. Or in other words, negative 1 copy of 2 to the n. And everything else that comes along for the ride, 3n squared plus 3n plus 1. Once again, if we think about what would the derivative have been, it would have been 3n squared minus 2n. The chain rule would have given me a log 2. But in a lot of ways, you're seeing that 3n squared still show up, and you're seeing the minus 2n still show up. So this is, once again, really behaving very similar to a derivative, but some terms look a little bit different, just slightly modified. So let's think about this as a derivative, but in fact, we really should think about the finite difference not as a derivative, but rather this word differential. And it's usually at this point in someone's calculus career not really clear what the difference between a derivative and a differential is. So let me describe that really quickly. A derivative is really the output of a function having been acted on by the derivative operator. This is a derivative. So the entire d dx acting on f is a derivative, and we compute that using the limit of the difference quotient. But something like df, which is in some cases, or in some interpretations, the numerator of the derivative, that's a differential. So when I write something like df dx, just the numerator is the differential, as well as dx, the denominator is as well, but the derivative is kind of the entire object. So that's kind of the difference between the two. If you want to think about it, really the finite difference plays the role of the discrete differential. So you can think about the numerator like up to the difference quotient, me taking a limit. The numerator of the derivative is really, f of x plus epsilon minus f of x, right? If I write out the limit definition of the derivative, whose limit is epsilon goes to 0, f of x plus epsilon minus f of x, all divided by epsilon, that numerator here really is playing the role of the differential. The denominator is playing the role of the differential of x. And then the whole thing is the derivative. So this finite difference is playing the same role here. It's just the subtraction of my shifted function with itself. So really the numerator of the limit definition. So with that said, the discrete derivative, right, and as I kind of talked about, a derivative is a ratio of a differential, or in our case, a finite difference, with the differential of the identity function. Now, what is an identity function? This is just the function that starts with x and ends with x. So don't worry about it if this isn't making any sense. But really what we should think is that the discrete derivative, you really do take the entire, this is playing my role of dx acting on a function, but rather than some d's, I have the deltas here. And delta x is a perfectly well-defined quantity. Let's think about how we would actually compute delta on x. Well, it's x plus 1 minus x, and the x's cancel, and you just immediately recover that delta x is equal to 1. The same thing happens in sequence land. If you wanted to compute delta n, that's n plus 1 minus n, the n's cancel, and you just end up with 1 as the denominator. So in some sense, if we want to compute the derivative of these objects, you should technically put a 1 in the denominator of these things, but let's all be honest, putting a 1 in the denominator doesn't actually change anything. And so I have this lovely proposition here that's like, by the way, you can write it as technically the derivative, which is not conceptually the same thing as the differential, but if you were to compute the two things, they are computed as the same value, as long as you're talking about finite differences. So finite differences and discrete derivatives are the same thing computationally, but conceptually, if you really want to be pedantic, the finite difference plays the role of the differential, and the derivative should be divided by the number 1. Okay, then we get to this next remark, which I love to make then, which is basically like, you know what, screw that, we're just going to use this delta symbol to mean both the finite difference and the derivative. So in sequence land, what is this remark actually saying? In sequence land, or in sequences, delta an is the derivative. It's the best we have for a derivative. And so we're basically going to treat it like the derivative for the rest of this chapter and the rest of our semester. So our next proposition basically says, it really does behave the same way. The finite difference constructs the local slope of a sequence. Or in other words, if I construct a line, this is playing the same role as the tangent line for functions and their derivatives. If I construct a line whose slope is defined by the finite difference on a sequence at a specific point n0, And if we go all the way back to our proposition on tangent lines, that n0 plays the role of x0. And so I'm going to take that n0, I'm going to subtract it from x, and I'm going to add the value of my sequence at that point. This line necessarily passes through, there are 2 points on the plot which this will pass through. It will pass through the point that I'm trying to construct the line at, n0 comma an0, so the input as well as the output, as well as the next point in the sequence, right? So in some sense, this term is the next point in the sequence. So this line, Lx, is the line which passes through one point as well as the next point of a sequence. That's the closest thing we can get in a sequence to a tangent line. There's no concept of tangent to just a sequence because you're not really trying to balance this line, against a mountainside or anything like that. There's just points. You can't balance on points. So what we do is we go to the next point and we say, okay, so it kind of hits both of those points and balances on the 2 of them. So we go to this next example, which is the quote-unquote tangent line to a sequence. We're going to consider the sequence defined by n sine x for n taking values in 0 to 10. And we can plot this sequence just fine, so let's go ahead and plot it. There it is. You could imagine if this were a continuous function of x sine x, then we'd have to plot it using some sort of continuous line which passes through all of these points that we're not going to pick up our pencil when we draw it. But because we're doing sequences instead, our points or our sequence values are just these discrete points. And so that's all we have when we have sequences. If we want to plot a sequence, you can think about this left one as a0, a1, a2, a3, and so on up to a10. And our line, suppose we grab a very special point, call it 2 comma 2 sine 2, so that's this very special point. We can construct a line, L of x, which is defined by the finite difference at a sub 2. So what is the finite difference at this point? And we'll multiply it by x minus the x value of the point, which happens to be 2 in this case. And I'm going to add a of 2, which happens to be y value at that point, 2 sine 2 in this case. What would the actual finite difference of something like n sine n look like? Well, it has a definition. Finite difference, you take your term, you add 1 to it, both cases of n, then you subtract the regular terms, n sine n. And in our case, we want to find this at 2, and so this will end up being, well, what is 2 plus 1? It's 3. Sine of 2 plus 1 is sine of 3 minus, well, what is 2? It's just 2 sine of 2. And so that's going to be our local slope here. And that's me calculating it explicitly down below. If I plug that in my calculator and look for an actual number to associate to that, you end up with negative 1.4 for your slope, as well as 2 sine 2 is 1.8. So if I plot that line, the line L of x equals negative 1.4 times x minus 2 plus 1.8, I get the line down here. And you can see exactly what this line does. It kind of balances on the point I care about, as well as the point directly after. Right? Here's the point I care about, there's the point directly after. We have no concept of tangent line because there's not really like the perfect balance on a single point. So by choosing our difference to be the forward difference, which is the one where you go plus 1 minus the original, we're saying let's move our line forward to balance between those 2 points instead. And so that's really the equivalent of the tangent line for sequences. And we also have this lovely property which we had for derivatives, which was that, well, derivatives were linear. Believe it or not, finite differences are also linear. And I realize it doesn't make sense still why I'm referring to objects as line-like when they behave like multiplication. But it's because, every time I draw a line, y equals mx plus b, this m is playing a pretty substantial role. So that's what we mean by linear. It's the multiplicative piece of a linear function. So when I say an object is linear, it kind of behaves like this multiplicative piece of a linear function. So we're going to focus on that and say finite differences are linear, but finite differences behave like multiplication. Which just means that we don't need a sum rule. We have products rules, we have quotient rules. We don't need a sum rule, right? We can just pass this over summations for free. So we grab that, we see a summation, we distribute it to both terms, an and bn, right? So the c's don't play any roles either. We just distribute directly to our 2 sequences. And that's how we would compute, the finite difference of 2 terms is the same as computing the finite difference of terms added together. And as I kind of expressed before with derivatives, why is linearity useful? Well, if I were over here at something like this, rather than trying to compute the finite difference of the entire thing, suppose that I already know the finite difference of an, bn, and cn, then I can just, when I'm computing the finite difference of everything, I can just compute them individually, right? Individually an, bn, and cn. So in this specific case, if I decided to say an was sine pi over 2n, suppose I said bn was nn minus 1 over 2, and cn was 2 to the n, I'm just going to give these to you now for free. We're going to see how to calculate these in the next section, but suppose that somebody hands you that the finite difference of an is root 2 cosine pi over 2n plus pi over 4. the finite difference with Bn was simply n, and the finite difference with Cn is 2n, then if I'm calculating the finite difference of kind of this giant sum of all three terms, I'm not forced to compute a brand new finite difference of all three and resimplify all of them, which is kind of what I'm saying down below here. We're not forced to do that. We just go ahead and compute difference of A, difference of B, difference of C, and I already know the difference of A, there it is, the difference of B, there it is, and the difference of C, there it is. So I'm really just I'm not forced to compute anything more special over summations. That's why we care about linearity. Okay, so that's actually going to finish this section. I'm going to jump slightly into the next section because the video has been a little fast today, so I want to get a little bit more done. We're going to move on to the common rules of the discrete derivative, or equivalently the finite difference. And we're going to recall the common rules for the continuous derivative first, and I hope it makes a lot of sense why I was referring to the derivative as a continuous derivative earlier, and now this one is the discrete derivative. We had linearity, which we've just covered, but in terms of the continuous derivative, we did have a product rule, which was pretty fancy to use. If we're taking a derivative of a product, that was equal to the derivative of one term, keep the second term the same, and then you add the first term times the derivative of the second. We also had a chain rule, we had a power rule, an exponential rule, logarithm rule. I omitted the quotient rule here, and I say that because once again, the proof of the quotient rule really depends on just applying the power rule and the chain rule and the product rule all together, and you do end up exactly with the quotient rule that you're used to. But we have all these lovely rules that we like to use to make our lives easier computing derivatives. Kind of the question becomes, is there anything we should do similarly for finite differences? And what I kind of say with this first remark is, no, we really shouldn't find rules for finite differences. The point of the rules for derivatives, and I think you've all experienced this if I ever had you complete derivatives using the limit definition, for complicated functions, the limit definition of the derivative is horrendous. And so all of the rules of the derivative only exist, these exist so that we can kind of sidestep the limit definition. These exist because limits are hard. And in particular, very hard for derivatives. Because the derivative relies on a limit definition. You know what doesn't rely on a limit definition? A finite difference. That's its definition. You take one term, you add one to the argument, and you subtract it from itself. These are all operations we know how to do very, very easily. So for example, I've got the case here. Suppose we have n times cosine n squared plus 1. You can immediately compute the finite difference of this by replacing this n with n plus 1, replacing this n with n plus 1. Okay, that's kind of the first term, an plus 1. And then you subtract an, which is just keeping it as n and n, keeping it as n and n. And that's it. This is the finite difference, and nothing more needs to be computed. You could go ahead and simplify it a little bit, but you don't even really need to, because the computer can handle this just fine if you needed to run any approximations or simulations with it. So you don't really need rules. And yet, let's jump back to the very first thing maybe I said, is that quote at the beginning of the book, where I say, mathematics is a game where you try to make the craziest statement possible. There's only one rule you can't lie. We're going to go ahead and make some crazy statements here. You may be mad at me for doing this. We're going to make crazy statements. We're going to see what's the best we can do for these derivative rules in terms of finite differences. And they can play like a little bit of a useful role, not when it comes to computing finite differences, but rather when it comes to computing the integral version, the antiderivative version. And so we will kind of have to use these, but it's just, we probably shouldn't use them for finite differences. We should use them because we can use their anti-versions for the version of integration that we're going to discover. Anyway, let's go through the product rule, and then we'll be done for the day. So the product rule for finite differences, it looks like the following. We're going to take the finite difference of a product, and the output is, well, it's almost like the derivative. I mean, we're really doing similar math here. We're going to have a finite difference of the first term of the product, and we're going to keep the second term the same. We're going to add the first term and take a derivative of the second. So this is the product rule for derivatives, right? Product rule for derivatives. For regular, quote unquote, regular derivatives. And then what else happens? In all these finite different problems, you get kind of a little extra. And so we end up getting the finite difference of both terms as our extra pieces. The finite difference of both of them gets multiplied together as a little extra piece, a little extra spice there for us. Let's go through the proof, because it's really not bad. If I want to calculate the finite difference, well, there's a definition for that, right? I'm going to replace both n's, both copies of n's, with n plus 1s. And then I'm going to subtract the sequences as they are. And that's all well and good. This is where I say this before. We could just do that and not need a rule or anything. But let's see if we can kind of force this to look like the product rule for continuous derivatives. Well, to do that, we should probably kind of force this to quote unquote look like delta an. Well, what does delta an look like? It looks like delta or an plus 1 minus an. What do we have right now? We have an plus 1. So we're just missing this minus an. We can do that. We can add it in there. We just have to pay a price, which is plus an, because these would naturally cancel each other. We're back to where we started. In this case, we don't want to cancel it because we want to group these two terms together, which is what I've done below. I've grouped the two terms together because when I group them together, I do have the finite difference. And so I'm just going to go ahead and play that game once, and that gives me the finite difference on A, and I can take this bn plus 1 and kind of distribute it to both terms here. So I do that. But now let's look at what we have left over here. So on the right-hand side, we've got an times bn plus 1 minus an times bn. Well, both terms have an an in them, so we can factor those two terms out. And what does this entire term look like? Well, it looks like an times bn plus 1 minus bn. But what is bn plus 1 minus bn? That's exactly delta bn, right? This is exactly delta bn. So we've ended up with here an an times delta bn. So what if we simplify this to, well, the product rule really looks like this, and you could probably leave it like that as well. That still kind of looks like a continuous product rule because we've got one derivative times one sequence and then the other sequence times the other derivative. The only slight modification is this left-hand sequence is an n plus 1. So it depends on if you're okay with keeping that as an n plus 1 or you want to kind of modify this further. If you do want to modify it further, we can say, hey, once again, delta bn happens to be bn plus 1 minus bn, and so we can kind of force the minus bn nature to show up at the expense of a plus bn, because normally these two would cancel, but we don't want them to cancel. Instead, we want to group those two terms together, which we do, and we call that delta bn. So we group those, call that delta bn, and we finish by distributing this delta an to both terms there. And what we're left with is kind of that product of two derivatives, or a derivative on each, as well as this term that truly does look like the product rule for continuous derivatives. So that's how we actually derive it, kind of a quaint little property. I'm going to stop there for today. I hope it's kind of fascinating that you can do so many similar things kind of in a modified calculus context. We're going to keep doing that in the next video, of course. I'll see you then. Bye.